Another class of power semiconductor devices that is very popular in power electronic systems is the IGBT. IGBT is an acronym for insulated gate bipolar transistor. The symbol for the IGBT is like this. So it has 3 terminals, just like the BJT or the MOSFET. You will see that the power side has the symbol which is similar to BJT, and the input side something like the MOSFET. That is because of the insulated gate. The control is voltage controlled, unlike the BJT which is current controlled. Here the IGBT is like the MOSFET, voltage controlled, has gate insulation, and because of that it has a high input impedance. So we have the 3 terminals C, G and E, collector, gate, emitter. So this is how it is named. So this is an N channel IGBT. Notice this arrow, and we can change the direction of the arrow and have a P channel IGBT. This is the emitter, gate, collector, and this is called a P channel IGBT. So this is the symbol that is used for the IGBT. Very popular device, and it can withstand very high voltages and high currents. And in most high voltage, high current applications, IGBTs are the ones that are the more prevalent power semiconductor switch that is used today. Let us visualize the various layers in the semiconductor. So you have the N-type, the P-type, N-type, P-type stack like this. So for the bottom NPN, you have the metal oxide insulation, you have the metallization, and this is where the gate terminal is brought out. And the top P type is connected to another terminal that is called the collector, and the bottom N type is connected to the emitter. So collector, emitter, and the gate. So let me duplicate this. The operation is very similar to MOSFETs, and you can understand it in this fashion. Let us make a break in this fashion. Let us split that top N type in this fashion and make the connection like this. So the N type is split. So this top N, PN, this PN is a PN junction. It is like a diode. So we can replace this portion by a diode in the equivalent circuit. This is the collector pin coming out, and this diode is connected to this bottom NPN NPN subsystem, and this NPN subsystem with the gate is like a MOSFET. So that portion is a MOSFET, so we can draw the MOSFET in this fashion. So this is the gate and this is the emitter. What is supposed to be the source of the MOSFET is the emitter here. So collector, emitter and gate. So this would form the equivalent circuit from this kind of a visualization. So from this you see the operation is very similar to that of the MOSFET. It is voltage controlled, has very high input impedance, and has all the behaviors like the MOSFET. There is one added feature. You see that in the case of the MOSFET, there is an internal body diode which is coming anti-parallel with the drain and the source. But in the case of the IGBT, there is a diode which is coming in series with the collector, and this has the feature where this device can block forward voltages when the gate is 0, and it can also block reverse voltage. This is a device which can even block a large negative voltage because of the presence of the diode. So the entire negative voltage will come across this reverse biased diode, and as a consequence you will see that this device is one of the very few devices that can block both positive and negative voltages. Let us now look at the static characteristics of the IGBT. Like in the case of the BJT and the MOSFET, let us draw the X and the Y axis. The X axis is the voltage axis, VCE, collector to emitter voltage across the IGBT, and the Y axis is the current axis, which is IC, or the collector current through the IGBT. So when VCE is swept from 0 to VCC value, you will see the static curves almost similar to that of the MOSFET, where you have a family of curves with the gate to emitter voltage being varied. It is a voltage control device. This region is the on state. So less than this region, where VCE is less than this ohmic drop or the saturation region, we call it as the on state. In the IGBT, there is an extra added part, which is the reverse part of the characteristic. Both the BJT and the MOSFET cannot handle negative voltage, means it cannot block negative voltage, whereas in the case of the IGBT, because we saw the presence of a diode collector to the internal MOSFET drain, it can handle reverse voltage too. It can block the reverse voltage, just like in the case of the diode, and this would be the peak inverse voltage value at which it will break down. So this is how the static characteristic collector curves of the IGBT look like, and this is the forward portion of the characteristic, and this is called the reverse characteristic. The transconductance curve VGE versus IC is very similar to that of the enhancement MOSFET, and here you see is the cutoff where you can say that this is the VGE threshold, which is very similar to the VGS threshold of the MOSFET. So these are the static characteristic, almost same as the MOSFET. In fact, for the dynamic characteristic, it is very similar to the MOSFET, not much changes. Here also you have the 4 states, which is the off state, the on state, the off to on state, on to off state. These are the 4 states, 4 periods. You have the delay time in both the transition states and the rise time and the fall time coming into the picture. Again, you have the conduction loss and the loss during switching, mainly caused during the TR and the TF times. So exactly similar to the MOSFET, there will be small changes with respect to IGBT to IGBT, just like you have in MOSFET to MOSFET, various MOSFETs. You can look at the data sheet to understand more about the individual specification values.